All right, welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell below. You'll get notifications for this series and a bunch of others on our channel. We're doing multivariable calculus. You probably know that by now. If you're down the list, we're 50 videos deep. We're in chapter 3, vector calculus. This is 3.4 Green's theorem. George Green is from England, so I'm actually, you're like, you never talk about all the other guys. Yeah, well, I'm Scottish and English through and through. So George Green was 1793 to 1841. He was a self-taught English mathematician. By age 9, he was working full-time in his father's bakery and then taught himself mathematics at the library, starting at age 9. He published Green's theorem in his 20s, I believe, but it didn't get much recognition. At age 40, roughly, he went to Cambridge finally and interacted with Lord Kelvin, which is the Kelvin temperature scale. And so Kelvin realized the importance of this and then republished it and circulated it, and Green's theorem and his work became the foundations for the work of Lord Kelvin himself, Stokes's work, Rayleigh's work, and most importantly, and the one you may know, is James Clerk Maxwell's work and the fundamental description of electromagnetic radiation and light. Was Green's theorem is the foundations of how to start phrasing these things. Green was working in a bakery as a kid. Let's cook up how to do Green's theorem. The one main thing that we're going to have here is we're going to connect line integrals to double integrals now using Green's theorem. What we're going to do first is the theorem that we're going to state right away is going to talk about these new curves, which are positively orientated, piecewise smooth, simple closed curves. See what? So let's go through these. Positively orientated is the new one, so actually I'm going to do that last. The other three, somewhere along the lines, hopefully I or someone else talked about these at some point when we talked about a parameterization of a curve. Closed is going to be the easiest one. Let's draw one. There, that means I have a closed curve C, which means the initial point and the terminal point are the same along the way. Piecewise smooth is going to say that technically what that means is the first derivatives are continuous. If we're parameterizing C as a position vector, then the derivative is continuous, which means that it has no cusps or sharp edges in the curve. Simple means that it has no loop, so you can't be the infinity sign, and you can't have any crossings. And a positively orientated curve is, what we mean by that by convention, is a single counterclockwise traversal of C. So regardless of where you start at this point. What you're going to do is do a single counterclockwise traversal and start at that point, and that's what we're going to call a positively orientated, piecewise, simple, closed curve. What makes this horrible is if you can't use Green's theorem and you're going to compute line integrals over positively orientated curves, you're going, and then all of a sudden I have a rectangle or something that I want to do the line integral over. I'm going to have to do, this way. That's positively orientated, this curve now. And now I have to break it up. This is going to be curve 1 positively orientated, curve 2 positively orientated, curve 3 positively orientated, curve 4 positively orientated. Then I have to find a parameterization for all 4 of these curves. We're going to do an example specifically of this. And then in each of those, we have to make sure that the parameterization goes from this point to this point, because that's the positive orientation. You can't make the parameterization go from here to here and just say, oh, so you have to make sure that you have it clever. So now your parameterization, the normal ones that you used, has to be a little bit more complicated because you have to parameterize that line, but going from here to here, not that way. So now this is the extra on line integrals of positively orientated. The parameterization has to say that it can't be just the description of that line. It has to be the description of that line, so that when you do the parameterization from t equals 0 to 2, you move from here to here, positively orientated. What? We'll do an example. But this is what we mean by positively orientated. Now let's give Green's theorem. All right, Green's theorem says, let C be a positively orientated, piecewise smooth, simple closed curve, and let D be the region bounded by that curve C. So we're going to have a positively orientated curve C, and then this will be the region D bounded by that curve C. What Green's theorem says is, if I have a vector field F which has its coordinates P and Q having continuous first order partial derivatives, they know this because we have to talk about them and it doesn't work all the time, but if you have that these guys are continuous, then we have that the line integral over c of p dx plus q dy is equal to the double integral over the region D of these difference of the partial derivatives dA. What this is saying is it can be treated, what this says is it can be treated as an analog to the fundamental theorem of calculus. Fundamental theorem of calculus, if I write it backwards, is the integral from a to b of f prime of x dx is equal to f of b minus f of a. If you now look and compare, on this side we have derivatives on the inside, derivative on the inside, and then double integral, single integral, but we have integral of derivative on the right hand side, and then on this side we have quantities involving just the original functions p and q or the original function f. So this is an analog to the fundamental theorem of calculus. What it's, and notice here is it's an expression in the original function f or the original function f, the p and q, and at the boundary only, at the boundary of the region D. This is computing the original function's pieces over the boundary C. This is the original function f at the boundary of our interval AB. And then this is talking about, the area under the curve of the entire thing from A to B. And this thing is also talking about an analogous version about the information about the entire interior can be computed as information about the original functions at the boundary, is what I'm trying to get at. Let's do an example of this. All right, we're going to compute a line integral now, and I'm specifically going to show you why Green's theorem is helping us a whole lot. Instead of computing that definition of a line integral, we're going to use Green's theorem to make it a whole lot easier. We have this line integral xy squared dx plus x cubed dy, where C is the rectangle with vertices 0, 0, 2, 0, 2, 3, and 0, 2. And of course we have to make it positively orientated. We're assuming this a priori if we want to use Green's theorem. What does that look like in the plane? That's going to give us, now, that's going to give us 0, 0, 2, 0, 2, 3, and 3, 0. So we're going to have this rectangular box is what we're going to get. And then I have to positively orientate it now, which says you go counterclockwise one traversal of that. This is now my curve C, and this is my region D, which is what I'm definitely going to want to. Do you see? This is Fubini's theorem and iterated integrals over a rectangle if I compute this as a double integral. Or we're going to have to compute a line integral of 4 curves. We now have, in fact, C1, C2, C3, and C4. I now have to parameterize 1. Not the way to do this. But I'm going to show you. Because you can, but just because you can doesn't mean you should. What are we going to do with that? Quickly, I don't even want to get into it, but parameterizing this, what we're going to do is I'm going to use my cheat sheet because we don't need to waste a bunch of time in the video, and this is not the way we're going to do it. I have to parameterize each one of these. So I have a C1, I have C2, I have C3, and I have C4 of these curves. C1 is y equals 0, and to make this positively orientated, x is t, and we're going to go from 0 to t to 2. That also coincidentally tells me that my differential dy is 0 dt, and this differential dx is equal to dt there. I have to compute the line integrals over all of these things. Holy crap, and I need those 2 differentials every time. And then we have to put the functions of all that business in there. Yeah. And then so I'm parameterizing these 4 curves now. C2 is now who? It's this guy, which is now, you can see x is the constant 2 and y is t, where now 0 is less than or equal to t is less than or equal to 3. Now if you see, if you move up, you'll move from there to there. That's where you're going to move from. And coincidentally in there, that says dx now is 0 dt and dy is equal to dt. For curve 3, to get this right positively oriented, I want to move from that point to that point. That says that y is definitely the constant 3, and then x is going to be equal to 2 minus t. I have to parameterize it that way because that says if t, and then I'm going to go from 0 is less than or equal to t is less than or equal to 2. That says when t is 0, x will start at 2, and y will be 3, and then by the time t gets to 2, it'll be 2 minus 2, and then it'll be 0, and it'll end up there. So it has to be positively orientated by parameterization. So if you were confused and you looked at some of those, that's why they parameterized this way specifically, because it has to be a positively orientated parameterization of that curve. And now it's broken into 4 freaking pieces. And instead I could just compute a double integral over a rectangle. But okay, I'll do this once. The curve 4 is what? Now it's going to be x is definitely 0. Oh, and my differentials are going to be dy is going to be 0 dt, and dx will be negative dt. And then this one, I'm going to get this, and then this y will be 3 minus t, the same thing, for 0 is less than or equal to t is less than or equal to 3. Now you can, I don't need my cheat sheet, I don't think. Oh yes I do, because I'm not doing that either. Oh, that's why you do it ahead of time, there. And then what are we going to do with this? This gives me the differential dx is 0 dt, and then luckily I don't have to compute all of those, but what is that going to give us? This is going to give me dy is negative dt. Putting all of this together now, that's going to give me this hot mess. Taking all those parameterizations and defining and computing this using the definition of line integral, we have the line integral over C, which is these 4 curves, positively orientated, is now going to be this over all 4 of those curves, that line integral. I split them up. The line integral over this one and this one and this one and this one. Then over all those parameterizations, we had all the differentials, dx's, and we had figured everything out. So then I can split this as the line integral over all 4 of those curves. Then once we put all those parameterizations in for each of those expressions, we got this. It was the integral from 0 to 2 of 0 dt. And then this one is going to be the integral from 0 to 2 of 8 dt. And then this one, cleaning it up, is going to be the integral from 0 to 2 of 9t minus 18 dt. And then the last one is going to be the integral from 0 to 3 dt. Luckily, sometimes when you do these don't even go away, and they've given you one where the parameterizations, the differentials aren't 0, so then those don't even go away. But in this case, they did, luckily. And then computing these ones, now I have to compute those integrals. This one, they're not too bad anymore. They're just polynomials. I use the power rule. I clean this up. I get a whole bunch of numbers. 6. I get 6 is the value of this line integral. Now let's use green theorem and do it in hopefully a lot fewer steps. Rephrasing, instead of viewing this as on the boundary C, we can look at the interior D, and this is a rectangle bounded by that curve C. What that gives me is the bounds are x is from 0 to 2 and y is from 0 to 3, and Green's theorem says that that line integral will be the double integral over D of the partial of q with respect to x minus the partial of p with respect to y. Remember, this is always p is in front of dx and q is in front of dy. What that will say is, what do I need? My function f is xy squared x cubed. That makes this p and this q. So I have to take the partial of p with respect to y is going to be 2xy, and the partial of q with respect to x is going to be 3x squared. Therefore, what that says is this integral over c of xy squared dx plus x cubed dy is equal to the double integral 0 to 2, the integral from 0 to 3 of the partial 3x squared minus 2xy dy dx, which is now just an iterated integral. I could do this in any order that I want. This becomes, holding x constant, the integral from 0 to 2 of, I'm going to integrate y, that's going to give me 3x squared y minus xy squared evaluated from 0 to 3 dx, which gives me the integral from 0 to 2 of 9x squared minus 9x dx. Again, what I'm going to get is I have 3x squared, and I'm going to put a 3 in there. I'm going to get 3 times 3 is 9, and then minus x, and then I get 3 squared, which is also a 9, and then I'm going to get 0, 0. So I'll clean that up. Now I integrate with respect to x. This is going to give me, by the fundamental theorem of calculus part 2, this is going to give me 9 over 3, or 3x cubed, minus 9 over 2x squared evaluated from 0 to 2, which is, guess what, 24 minus 18, which is 6. So you can phrase and have to parameterize all of those curves and get that and use the boundary information to compute that line integral, or we can now have the connection between Green's theorem and have that we can compute this as a double integral over the region bounded by the curve of these partial derivatives, which is much nicer. Please subscribe right here, hit the notification bell. I'll see you next time.